Welcome to Maths with EJD. In this video, I'm talking about homogeneous linear systems under systems of differential equations. Having earlier identified that systems of differential equations can actually be either homogeneous or non-homogeneous. So first of all, a homogeneous linear system is a system of linear equations of the form AX equals 0. Usually we would have AX equals B, but in this case, we have AX equals 0. So where A is a matrix, X is a zero vector, X is a vector of variables. X is a vector of variables. Then, well, this 0 here, this 0 is a special kind of 0, and it is the zero vector. It is a zero vector. Okay. Now, with that said, um, the system is homogeneous because the right hand side, the right hand side of the equation is 0. Okay, so a typical form, or rather a typical problem in this context is to find the solution vector X that satisfies this equation. For example, consider the system that's 1, 2, 3, 4, then x1, x2 equals 0, 0 this way. So this actually this translates into the following system of equations. Okay, that's x1 plus 2x2 equals 0, and then 3x1 plus 4x2 also equal 0, like this. Okay, so to solve, we can find the null space of the matrix A. So first, we find the determinant of A. I've done a lot of these kind of things under my very first playlist, which is on matrices. So if you need a very deep understanding of matrices, you can go through the over 20 videos or so on the matrices playlist. So first, we find the determinant of A. So that means we need that A. That A is simply the determinant of 1, 2, 3, 4. And that is easily 4 times 1, this, minus 3 times 2. 4 times 1 minus 3 times 2. That is 4 minus 6. And that is simply minus 2. So in this case, that's the determinant. Okay. So we say that since the determinant is non-zero, if the determinant were to be 0, it would be something else. But since the determinant is non-zero, okay, this system has only the trivial solution, x1 equals 0 and x2 equals 0. So, but if it were otherwise, then that won't be the only solution. So in that case, we can say, thus, the solution is the trivial solution. Solution is a trivial solution, meaning no non-zero vector, no non-zero vector satisfies this equation. Okay, so if you try to even use the conventional methods, right? So we multiply this first one by, say, by 2, and we have like 2x1 plus 4x2 equals 0. And we now have 3x1 plus 4x2 equals 0. So if you subtract, we have x1 equals 0 easily. And by the time we put that one back, we also get x2 to be equal to 0. So you see, that actually works. Even so, once the determinant is non-zero, then you can be sure that the solution is only trivial. Okay? So we have that like that. So let's talk about eigenvalues and eigenvectors. I've talked about this a lot of times under different topics. So let's revisit that idea because it's very useful here. So you see that generally, if you want to be very good at math or computing, you have to be very solid with algebra, especially talking about linear algebra, matrices, because most of the coding you do and everything is based on the idea of linear algebra on matrices. So we say that an eigenvalue and eigenvector are associated. They are associated with square matrices. So you don't talk about eigenvalue or eigenvectors for matrices that are not square, for triangular matrices, that is. So they're associated with square matrices. And then we say that for a matrix A, an eigenvalue lambda and an eigenvector V actually satisfy the fact that AV equals lambda V. Okay, so this is always there. But then to find the eigenvalues, we solve the characteristic equation. I think we did an example in this line here in the previous video. We solve the characteristic equation, which is the determinant of A minus lambda I equals 0. Okay, so where I is the identity matrix, An identity matrix is the equivalent of 1 in normal numbers, right? And then lambda represents the eigenvalue. Okay, now with this done, let's look at an example. I think probably the same example we did before now, I believe. So consider A, which is 4, 1, 2, 3. So here, the characteristic equation is the determinant of a minus lambda I, which is equal to, so determinant of a is 4, 1, 2, 3, okay, minus lambda I. So say that's minus lambda. I is 1001 for a 2 by 2. If it's 3 by 3, then that'll be 1000 100001, like that. So that this will be equal to the determinant of 4123. Okay, 4123 minus lambda 0 lambda. Okay, just to drive the point home, actually. So here we have the determinant of 4 minus lambda 1, 2, 3 minus lambda. Okay. Of course, this whole thing is 0. I should say that. So the whole thing is 0. This is 0. Okay. So this is actually 0. So we have 4 minus lambda, 3 minus lambda, minus 2 equals 0. So 4 times 3 is 12. 4 times minus lambda, that's 4 minus 4 lambda, minus lambda times 3, that's minus 3 lambda, then plus lambda squared minus 2 equals 0. Okay, so we can rearrange this to have, we have lambda squared minus 7 lambda plus 10. Okay, 12 minus 2 is 10. That's equal to 0. So we can try to factorize now, or we can use the so-called almighty formula, okay, where we know that lambda is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. And, following from lambda squared minus 7 lambda, all right, plus 10 equals 0. So the coefficient of lambda squared, that is our a. So a is 1. B is the coefficient of lambda, that is minus 7. And lastly, c is the constant, that is 10. Okay. So if you do that, then we say that lambda is equal to minus 7 plus or minus square root of b squared, that's minus 7 all squared, minus 4 times 1 times 10, okay, all over 2 times 1. So that lambda is equal to 7 plus or minus square root of 49 minus 40 all over 2. Okay, all over 2. And then lambda is equal to 7 plus or minus square root of 9 all over 2. So lambda now is equal to 7 plus or minus square root of 9 is 3 all over 2. So lambda is 7 plus 3 over 2. That's lambda 1. Lambda 2 is 7 minus 3 all over 2, plus minus, right? So lambda is equal to 7 plus 3 is 5. 10 divided by 2, that's 5. And the second one, lambda 2, is 7 minus 3, 4 divided by 2. So these are the values of our lambda, okay? So these are the eigenvalues. These are the eigenvalues which we are looking for. So these are eigenvalues, okay? Now, it's important to know that for each eigenvalue, we substitute back into a minus lambda I v equals 0 to find the corresponding eigenvectors. Find the corresponding eigenvectors. Okay. So we go for that, and we can say that for lambda 1 equals 5. Okay. So we have a minus 5i v equals 0. So what this simply means is that we have okay, let me set that up. A is again 4, 1, 2, 3 minus 5i, of course that'll be 5005. Not determinant this time around. Okay, so more like this multiplied by v. So v in this case would be v1, v2, which we are now looking for, and all of this is equal to 0. So that means we have 4 minus 5, that's minus 1. 1 minus 0 is 1. 2 minus 0 is 2. 3 minus 5 is minus 2. Then V1, V2 equals 0. So if we do that, so we have V1, V2. So because we have two rows here, right? V1, V2 twice, and then invert minus 1, minus 1, 1. Then here we have 2 minus 2. So the all this is equal to 0, 0. If you that's a vector actually. So we have minus V1 plus V2. Then we also have 2V1 minus 2V2. So this is 0, this is 0. So anyhow you look at it, the two are basically the same kind of thing, right? So anyone you pick, they're basically the same because um you now have minus V1 plus V2 equals 0. That simply means V2 is equal to V1. Okay. If you also take this other one, which is not necessary, by the way, or, well, just to be sure, right? So you have 2V1 minus 2V2 equals 0. So that means that 2V1 is equal to V2. And again, V1 is simply equal to V2. So if that is the case, we have our eigenvalue already. So we can just say, thus, thus eigenvector, the eigenvector, the eigenvector, because they are both the same, right? The eigenvector corresponding to lambda 1 equals 5 is any scalar multiple. So actually any scalar multiple of v equals 1, 1. Okay? That's the eigen, because I mean v1 is equal to v2. So any other thing that can multiply this, it can be 1, 1, 2, 2, minus 1, minus 1, 0, 0, anything like that, as far as they are the same. So that's for lambda 1 equals 5. So what about for lambda 1 equals 2, I think? Yeah, for lambda 2 now, which is equal to 2. So we have a minus 2i v equals 0. So that will now be a, which is 4, 1, 2, 3, minus 2, 0, 0, 2. Okay, all that into another v1, v2, which is equal to 0, 0. That's how the setup looks like. Yeah, so we now have this to be 4 minus 1, 2, 1 minus 0 is 0, 2 minus 0 is 2, 3 minus 2 is 1, like that. So that we have this v1, v2, all of this is equal to 0, 0. Again, we have v1, v2, v1, v2. Then we bring 2, 0 here, and we bring 2, 1 here. Okay, so this is equal to 0, 0. I hope this is correct. Let me see. 4 minus 2 is 2. 1 minus 0. Okay, I think I made a mistake here. Because I'm already looking at it like it's not looking like what I should have. Okay, yeah, that works now. So 4 minus 2 is 2, 1 minus 0 is 1, 2 minus 0 is 2, 3 minus 2 is 1. Okay, good. So we have 2v1 plus v2 equals 0. In both cases, 2v1 plus v2 is equal to 0. Okay, so you can just pick one of this. So we have 2v1 plus v2 equals 0. That means that v2 is equal to minus 2v1. So whatever V1 is, V2 is minus 2 multiplied by that. Okay, so we can say, so V in that case is, so if V1 is 1, then V2 is minus 2, basically. Okay, so that's minus 2. In the first case, we got 1, 1, right? So this will be minus 2. So you can conclude. So the eigenvector, the eigenvector corresponding, how did we conclude this one? Corresponding to lambda 2 equals 2 is V equals, based on this, that V2 is minus 2 multiplied by V1. Okay. So if V1 is 1, V2 is simply minus 2. So any scalar multiplicity of this is correct. So if you multiply by 2, you have 2 minus 4, like that. So that's all we have right there. So those are the ideas of eigenvalues and eigenvectors. So overall, right, overall, we have the eigenspace, something like you can say this is when it's 5, right? 5 together with 1, 1, okay? And 2 together with 1 minus 2. So you have the eigenvalues first and then the eigenvectors together with them. So something like that. Now, having talked about this, right, can we switch gear and talk about something different? Okay, so let's talk about solutions. Solutions using the matrix exponential. Solutions using the matrix exponential. Okay. So the matrix exponential, which is e raised by at, is used to solve systems of linear differential equations. Okay. Particularly in dynamical systems. Okay. For a linear system, the x dt equals ax. The solution is given by x of t. The solution is given by x of t equals e raised power at multiplied by x0. Okay, so that's a standard where e raised power at is the matrix exponential, Okay, now if the matrix A is diagonalizable, I talked about diagonalization on the matrix playlist, so you want to check that out also. If the matrix A is diagonalizable, okay, this is computed. This is computed as e raised power at equals p e raised power lambda t p inverse. Okay, that's how we compute that if we have a diagonalizable matrix. Okay, so where again this lambda now is a diagonal matrix, diagonal matrix of eigenvalues A, and P is the matrix. So you see that we need eigenvalues and eigenvectors, and P is the matrix of eigenvectors. Okay. Then that leads us to look at the example. Okay. Consider the system x dot equals ax. Okay. Where of course x dot is dx dt, where a again is 4, 1, 2, 3, the same thing we've been doing, 4, 1, 2, 3. So remember we found the eigenvalues of it. We find the eigenvalues of A are lambda 1, lambda 2 equals 5, comma 2, and the eigenvectors V1, V2, we also found those ones to be 1, 1, 1 minus 2, if you remember. Okay. So these are going to help us to go on. So now we can now say the matrix P. The matrix P that's the matrix of eigenvectors. The matrix P is simply P is 1, 1. You know, the matrix P is simply V1, comma V1, V2, okay? V1, V2, which is 1, 1, 1 minus 2. That is matrix P. So if you did not have this, though, you have to find the eigenvalues and eigenvectors before you can come all this way. But thankfully, we found that before. So on the other hand, right, the matrix, the matrix gamma, yeah, is this gamma or lambda now? I think it's gamma also. The matrix gamma is, what did you call that matrix again? Where is a diagonal matrix. So, and it is the diagonal matrix of the eigenvalues, by the way. So that will be, this equals lambda 1, 0, then 0 lambda 2. That's how we do this. So this is 5, 0, 0, 2. Okay? 5, 0, 0, 2. That's really important to note. So it means that the first step you want to take, if you are using exponent of matrix, or what do we call that now? Matrix exponential, exactly. If you want to use matrix exponential, lambda, the eigenvalues and eigenvectors are really important. So 5002, okay, that's that. So with this now, what do? We say thus, um, thus, okay, e raised power at, which is equal to p e raised power lambda t, p inverse, is simply the same thing as e raised power at, which is equal to p. That's 1, 1, 1 minus 2. Then for this now, we have how do we put this now? Okay. This is like e. Okay, I mean, based on the fact that we have lambda t there, so that would just be e raised to power 5t, 0, 0, e raised power 2t. So that's how that comes out, based on this now. So it's more like we have e raised power 5002 is like e raised power 5t, 0, 0, e raised power 2t. This into 1, 1, 1 minus 2, okay, 1 minus 2 inverse. All right, so we can tidy that up. The inverse of a 2 by 2 matrix is easy to find. So we have e raised to power at equals 1, 1, 1 minus 2, e raised to power 5t, 0, 0, e raised to power 2t, into, for this now we have 2 over 3, 1 over 3, 1 over 3, and then minus 1 over 3. That's the inverse of that. So with that in place now, we have just a few things to talk about. Let's switch gear now, and then let me switch this one over to this, where I now say that we now talk about diagonalization and fundamental matrices. Diagonalization and fundamental matrices. Okay. So we say that a matrix A is said to be diagonalizable if there exists an invertible matrix P such that, so an invertible, like that matrix now, we could find its inverse. That's why it is invertible, such that A is equal to P, A is equal to P gamma P inverse. Is this thing gamma or pi? I've forgotten what this should be. Okay. So, well, so where, or is it alpha capital? Where alpha is a diagonal matrix. Pardon me for just calling it different things. Right now, I do not remember what it is. I think it should be alpha, where alpha is a diagonal matrix. of eigenvalues. Okay. So the matrix P is composed of the eigenvectors of A, just like what we did up there right just now. Okay. So we can go on and talk about the fundamental matrix. So the fundamental matrix solution, fundamental matrix solution, okay, to a system, the x, the t equals ax is phi of t, which is equal to e raised power at. Okay, this is the fundamental matrix solution. And if A is diagonalizable, okay, I mean, we've given the condition for something being diagonalizable. So this is the condition that it can be diagonalized, okay? So, and if A is diagonalizable, right, this simplifies, to phi of t equals P e raised by alpha t P inverse that we've seen before. So that's the fundamental matrix thing. So finally, right? Okay, this sounds like a repetition, but let's just go through with it. Okay. So again, an example, the same example we did before, just for emphasis now. So for for the matrix, for the matrix A, which is 4, 1, 2, 3. Okay, we already know. We already know the eigenvalues. We already know the eigenvalues. Lambda 1 equals 5, lambda 2 equals 2, and the corresponding eigenvectors and the corresponding eigenvectors. That's V1 equals 1, 1, and V2 equals 1 minus 2. Okay, so we can now say that matrix, the matrix P, the matrix P. Okay, let me just repeat them, right, for the fun of it. The matrix P, which is 1, 1, 1 minus 2, and alpha, which is 5, 5, 0, 5, 0, 0, 2, 5, 0, 0, 2 were computed above, right? Were computed above. All right. Thus, the fundamental matrix, the fundamental matrix solution, phi of t is phi of t equals 1, 1, 1 minus 2, e raised power 5t, 0, 0, e raised power 2t, okay, into 1, 1, 1 minus 2 raised power minus 1. So the fundamental matrix solution now is just like what we got before. This is 1, 1, 1 minus 2 into e raised power 5t, 0, 0, e raised power 2t into, again, 2 over 3, 1 over 3, 1 over 3 minus 1 over 3. So with that, we come to the end of this very interesting part, talking about homogeneous linear systems. So as a parting gift, we want to practice the following. Let's practice with some of this. So one, solve the homogeneous system, solve the homogeneous system 2 minus 3, 4 minus 6, x1, x2 equals 0, 0. Okay, that's one. Two. Mm, okay, find the eigenbasis and the eigenbasis for A equals 6 minus 2, 2, 4. What that simply means is that find the eigenvalues and the eigenvectors. That's just what that is about. Okay. Then 3 now. Compute e raised to power at for A, which is equal to 0, 0, 1, 0. Okay. What else? Then let's say 4 now. 4, solve dx dt equals ax, where A is 3013 and x of 0 is 12. Okay, that's like the initial condition or something like that. What else? I think I should make it up to 5, right? So let's do this. 5. Find the fundamental matrix and the fundamental matrix for dx dt equals 2112x. Okay, so let me have your answers in the comment section, either on Facebook or on YouTube. Let me also know how helpful these videos are for you. And if you need me to teach a topic or solve a problem, feel free to let me know. Then if you have subscribed, please thank you for that. And if you have not subscribed, please go ahead and subscribe. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And don't forget to share and like so that other people, then also comment. I get to engage. Some people, sometimes I make mistakes and people find it out and we're able to interact like that. So make comments, ask questions, and let me know if you need something as far as lies within my power. As far as all of this is concerned, we can sort it out. Till I come your way again, keep doing maths right. Bye.